Welcome to the movie about Newton's second law. In this first little movie here, we will show a spring force on a ball bearing. But we will use different forces by rotating the car keys on the same ball bearing. And if we let the movie roll, you will see the first time I will use the spring force and the ball bearing rolls this distance. When I rotate the car keys, the spring force will be bigger. And you will see that the ball bearing will roll a greater distance. Well, next we will use spring force on the same ball bearing. On the ball bearing end. Now this time we will use different ball bearings, but the same spring force. So first ball bearing is a big one, and he rolls distance UC. Second, we use a smaller ball bearing. I get it here. The smaller ball bearing, same spring force, and of course, as you will guess, it will roll a much greater distance. Well, now we have Newton's second law, which is that the acceleration an object receives is dependent upon the force. The larger the force, the more acceleration the object will have. And the acceleration is inversely dependent upon the mass. So the bigger the mass, the smaller the acceleration. Put it together, acceleration is dependent on the force divided by the mass. Or the force is dependent upon mass times acceleration. Now we want to make that into a formula, and normally we need a constant, but Newton was lucky because the force was not yet a physical quantity used yet. So he could make that 1 Newton equals 1 kilogram times 1 meter per second squared. And let's look at it in more detail. We have several forces on an object here, it's just random example. And all the forces together will give a net resulting force. It's this net resulting force which has the formula we had before. Let's go a little bit back. The force equals the mass times the acceleration, which is Newton's second law. So all the resulting forces is the sum of all. The resulting force is the sum of all the forces acting upon the object, which means that we write Newton's law, second law at least, as the resulting force is the mass times acceleration. And look upon the vector sign. But we will divide it in two axes, so we have an x-axis and a y-axis, because it's easier for the forces to calculate our examples using it in two axes, x and y. You'll see next with the acceleration. Here again, 1 Newton is the force to give an object with a mass of 1 kilogram and acceleration of 1 meter per second squared. And we'll look at a few examples. The first example is an easy one. On a mass of 50 kilograms we have a net force of 250 newtons, which is the acceleration. What is the acceleration? We have a mass of 50 kilograms and a resulting or a net force of 250 newtons. And asked is to find the acceleration. The solution, we have Newton's second law, which means that the acceleration is the force divided by the mass, which gives us that the acceleration is 250 newtons divided by 50 kilograms is 5 newton per kilograms, or 5 meter per second square, which is the same thing as we will show at the end of this movie. A car which has a mass of 1,500 kilograms drives on the freeway and has a speed of 110 kilometers an hour. He accelerates to 120 kilometers an hour during 5 seconds. There is a frictional force of 500 newton. Draw the forces at the center of mass in this picture. Well, here's my nicely drawn car, and we have a gravitational force downwards and a normal force upwards. Then we have the force of the motor, which accelerates the car or drives it on a constant speed depending on the situation, and we have the frictional forces. Because the car accelerates, which means that the motor force is bigger than the frictional force, and we have a resulting force and as a result. So the motor car less the frictional force give the resulting force, which gives us, we have to use the sum of the vectors. So all the vectors we're gonna add together, but watch out, it's our vectors. So a vector, sum of vectors, is not just counting up all the forces. No, we go look per axis, and then in the x-axis we have the frictional force and the motor force, which is the mass times the acceleration in the x direction. And we can do the same in the y-axis, where we have the normal force and the gravitational force, which is also mass times acceleration, but this time in the y direction. So we split up. In fact, we calculate with two net forces, one in the x direction and one in the y direction, which makes calculations much easier. Because in the y direction we have no net resulting force. It's zero. The car does not start to fly or does not sink into the road. So the net force is zero there, because the acceleration is zero. In the x direction it's a little bit different. We have our given factors, which is the initial velocity is 110 kilometers per hour, and which means it's 30.6 meters per second. The end velocity is 120 kilometers an hour, which means 33.3 meters per second. And the time is 5 seconds. Well, we go back to our kinematic formula, which means the speed is the acceleration multiplied with time plus the initial velocity, which gives us this. A is v minus v0 divided by t is 33.3 minus 30.6, the two speeds difference, divided by 5, which means 0.45 meters per second squared as the acceleration. So we have the acceleration, which means that the net force is the mass times this acceleration. Newton's second law we have here. So 1,500 kilograms times 0.54 meters per second squared is 8.1 10 to the second Newton, which means 810 newtons. What is the force of the motor? Because this is the resulting force. Now the force of the motor has to be bigger because it also has to conquer the friction force, which means that the friction force and the motor force, vector speaking, and look at the vector signs. We have here the vector signs, is the resulting force. Now, which means that the motor force is equal the resulting force minus the friction force. But friction force is in the negative direction, so when we fill in our numbers, we have for the resulting force 810 plus 500 Newton, because we have to conquer the friction force. Remember the friction force in our drawing. When I go all the way back, you see that friction force is in the opposite direction of the motor force, so it has a negative sign. And we go back all the way, and here we have, so which means that we have 1.3 times 10 to the third power Newton. And last example, the skydiver. We had in the previous movie, airplane and skydiver again, which means that the gravitational force, which is m times g, our gravitational field force, gives that the gravity is, at the moment he jumps, the resulting force, which means that at the moment he jumps, and we have not yet speed to have a frictional force, we have m times g is m times a. M we can drop, so we are left with g is a, which means that Newton per kilograms is the same as meters per second squared, like said earlier in the movie. Now, time for you to get some exercises on this.